In this video, we're going to wrap up chapter 7 by introducing the kinetic energy, and then we'll also talk about the work-kinetic energy theorem. So we've seen that when you have a force that changes with displacement, then you calculate the work by taking the integral from some x initial to some x final of the net forces acting on the system. So from Newton's law, we know that the sum of all the forces acting on the system is equal to the mass times the acceleration. So I can replace the sum of the forces here by the mass times the acceleration. And then if I do this integral, I can write the acceleration as dv by dt. And so solving this equation right here using chain rule, so I can write dv by dt as dx by dt times dv by dx. And so this dx is going to cancel with this dx. Dx by dt is equal to v. And so you end up with this equation right here. So the key point here is that the work can also be written in this form. It's just 1/2 times the mass times the v final square minus half times the mass times the v initial square. So at this point, we're going to introduce a quantity called the k value. So the k value is called the kinetic energy. And the kinetic energy is given by this equation. It's 1/2 times the mass times the velocity square. So with this definition of the kinetic energy, I can go back and write this equation. So I can just say that the work done is equal to the kinetic energy final minus the kinetic energy initial. Or we could say that the work is just a change in the kinetic energy. So this is a very, very useful equation. So we're going to use this equation a lot to solve problems. So if I know what the change in kinetic energy is, then the change in kinetic energy is just equals to the work. All right. So basically, the work-kinetic energy theorem simply says that when work is done on a system, and the only change in the system is the speed of the particles, then the net work done on the system must be equal to the change in the kinetic energy. So if you assume that there is no frictional forces in the system, so all the work is just going to be used to increase the kinetic energy for a system. All right. So now we're going to look at example number 7.6. So in this example, we have a block that is pulled on a frictionless surface. And so it tells us what the mass of the block is 6.0 kilograms. And then it says that it starts initially at rest. So that tells me that the initial velocity is 0. Then we know that this is pulled with a force that is 12.0 newtons, with this force right here. So what we're going to do is I want to find the block's speed after it has moved through a distance of 3.0 meters. So again, this is the problem right here. So I want to set up the system here. I identify all the forces acting on the system. So I have my normal force, I have my m times g, I have my applied force. And so this is what we're going to calculate. We want to calculate the final velocity. So the displacement is this distance from here to here is delta x, which is the 3.0 meters. So again, if you remember, we said that because the normal force and the force of gravity are pointing in the y direction and the displacement is in the x direction. So when I calculate the work is going to be contributed, it's going to be produced only by the applied force. So the normal force and the force of gravity are not going to produce any contributions. All right. So if I use the equations that we've just derived, I can say that the work is a change in the kinetic energy, which is kinetic energy final minus kinetic energy initial. So the kinetic energy final is just 1/2 times the mass times v final square. The kinetic energy initial is 0 because we are told in the problem that the block starts from rest. So at t equals to 0, the initial velocity is just equal to 0. Now, so I can calculate my v final is 2 times the work divided by the mass. So again, from here, if you just solve for vf, you get VF as the square root of 2 times the work divided by the mass. But we know that the work is given by the force times the displacement, so F times delta X. And so if I substitute that into this equation, I get this expression for my final velocity. Now, if you go ahead and plug in the numbers, you can calculate your final velocity as 3.5 meters per second. So now we're going to introduce a different form of energy. This is called the potential energy of a system. Now we can think about the potential energy of a system as the work done by any object due to the gravity, due to the Earth, the force of gravity produced by the Earth. So again, if you look at this picture here, suppose that we take an object here from some initial height, y initial, and we're going to move it from some initial height, y initial, to some final height, y final. Then this would be the change in the potential energy. It's just mass times gravity times y final minus mass times gravity times y initial. So again, if you want to write this in terms of vectors, I can calculate my displacement vector. So the displacement vector delta r is just y final minus y initial, and this is in the j direction. Then I can calculate the force. So the force that is acting on the system is just the applied force. So the applied force here is just the force of gravity, is my m times g. And this m times g is also pointing in the j direction. And so if you put all of this together, you can calculate your work done as just mg y final minus mg y initial. So now we can also define a new quantity called the potential energy due to gravity. The potential energy due to gravity is just given by m times g times y. And so in this case, I can say that the work done is just a change in the gravitational potential energy. So something that we're going to remember here is that the gravitational potential energy only depends on the vertical height of an object above the Earth's surface. So again, we can write down our work done as just a change. So when we move something in the vertical direction, the x final and the x initial do not change. So I'm only looking at the change in the y direction. All right. Okay, so now we're going to introduce one more type of energy. It's called the elastic potential energy. And this is just the energy of a spring system. So basically, if you look at a spring at x equals to 0, so it means that this is the length of the spring. And then when you compress it by some distance x, you store energy on the spring. And that energy can be calculated as 1/2 times the k value times the x squared. So in this example, you can stretch the spring to some maximum value. And then once you release it, the energy is going to be converted into kinetic energy of this mass right here. So this is going to increase the velocity of the mass. So using this equation, we can also define the elastic potential energy, which is the spring potential energy is just given by 1/2 times k times x squared. And so we can also say that the work is just the change in the spring potential energy. Now the elastic potential energy, so what this picture shows you, it shows you what the different energy diagrams of a system. So if you look at this picture right here, so in the first picture, before the spring is compressed, notice that there is no energy in the system. So the kinetic energy is 0, the potential energy is 0, and the total energy is also 0. Now, when the spring is partially compressed, the total energy of the system is elastic potential energy. So moving from here to here, we've applied a force, we've compressed this by some amount x, right? But at this point, the mass is not moving yet, so the mass is still at rest. So because the mass is not moving, all the energy is going to show up as potential energy of the system. So you can see that in this picture here, the kinetic energy is still 0. The potential energy is the same as the total energy. And then when when the spring is compressed to the maximum value, then the potential energy becomes maximum. And the maximum potential energy, again, is also equals to the total energy of the system. There is no kinetic energy of the system. Now, after the block is released, the elastic potential energy in the system decreases and the kinetic energy increases. So now you can look at this picture right here that the energy is just changing between, so part of the energy is going to show up as kinetic energy, part of the energy is going to show up as potential energy. Now, after the block loses contact with the spring, the total energy of the system is just kinetic energy. So again, by the time that the block passes through this point at x equals to 0, so when x equals to 0, the displacement is 0, there is no potential energy. It means that all the energy has been converted into the kinetic energy of the spring. So this picture shows you how the energy changes from one form to another. But again, the total energy of the system is not changing, but the point is that the energy is just changing from one form, so from potential energy to kinetic energy.